And so at the end of the last video, I thought somehow that I was done, but I wasn't. More. 1, 2, 3 more. So let's get them done. Sorry about that. 2 identical steel balls, S and T. So T is coming in this way, and this is the moment of impact, and then after the impact, it leaves this way. S is coming in this way, and then after the impact is going this way. The velocities of the 2 balls before and after the dashed lines show the speeds of the balls are the same before and after the collision. All right. So they want to show which letter represents the direction of the initial momentum of ball T. All right. Well, the initial momentum of ball T is going to be this direction, right? Down and to the right. So D would be the correct one. So I'm going to go with like that. All right. Which letter represents the final momentum of T? Well, that would be that would be B, wouldn't it? In fact, I would say they're perpendicular to each other, and they're the same length, aren't they? All right. So here's the deal. What's the I'm going to bring this up. What is the change in direction, though, or the change in momentum? Well, this is what it was. It changed to this. The change is actually straight up. If you think about it, the horizontal component of this thing's velocity never changed, but the vertical switched direction. So all of the change in momentum here is going to be straight up. That's why A was my answer here. So we're going to use a similar argument set up here. So we'll do this whole area here for S. So S, so which that represents the direction of change in momentum for S. So S's change would be straight down because it came in this way. So left to right wasn't affected, but it had a vertical component that went from up to down. So its change would be like this. What letter? Okay, now it's just a vocabulary question. So they just devolved in. Now they're asking us about for ball T. What about the impulse? Well, the impulse is the change in momentum, so it's the same. They're just verifying that you know that impulse is another phrase you can use for change in momentum. So that's why this is this and this is this. For S real quick, it came in, so let's just see how we got the downward arrow. So S came in like this. So here was the collision. Its momentum was that way. And then from the collision point afterwards, its momentum was this way. That's a change from beginning to end, that's straight down. All right, rank the magnitude of the momentum before they collide. Okay, so we're going to have to add them together as vectors. That's the only thing we got to be careful of. So, for example, here, I got to be careful. I don't know if I did that or not. We're going to find out if I did this right. I'm not even going to pretend I didn't write that down. So this would be 6 this way. Let me write it down here. So it would be 6 horizontal due to this, combined with 8 upward. So that would be, this would be their combined momentum. Whatever 8 squared plus 6 squared is, take the square root. So 64 plus 36, it's 100 squared 10, so that's 10. So this has an original momentum of 10 kilogram meters per second. This has 6 and 8, so it's also got 10. They're going against each other here. In fact, they're identical and going against each other. So this is 0. This is, say, negative 8 and positive 8. This we'll say is negative direction to the left here. So this is negative 9. This is positive 6. So here the initial momentum is negative 3. Magnitude-wise, you could just call it 3. So I should have A and B being the same, tied up for the same. Not sure why I don't. And then C's definitely last, and D would be there. So I should have A, B together, and then D, and C, if they just want magnitude. Rank the magnitude of the momentum of the two ball systems after they collide. If the balls stick together, I could care less if they stick together actually in this case, because the conservation of momentum says that the momentum is always conserved for the system. So if all I do is consider these two spheres, it is going to be the same. So AB, then D, and then C. These two are going to collide and probably both stop, for the momentum still going to be zero. If they stick together, yeah, they're going to definitely stop. These two are going to stick together and then move really slowly to the left. In fact, what's 3 plus that's 5, so 3 divided by 5. They're going to move to the left at a speed of 0.6 meters per second. They'll have the same momentum, but that's either way. These two are going to collide, stick together, and move off in this direction. That looks like a 45, but it's not, because 8 should be longer. But they're going to go off in that direction at a certain speed, at 10, with a momentum of 10 kilogram meters per second. Then they say rank the magnitude of the momentum of the two-ball system after they collide elastically. It doesn't matter. Momentum is always conserved. You would have the exact same answer. It would look different, possibly, but it's going to have the exact same answer. The momentum before and the momentum after. Momentum is always conserved as long as there's no outside forces. All right, now the last one. The figure below, two balls traveling in different directions are about to collide. The balls have the same size and shape, but they have different masses and are traveling at different velocities shown. Identify the closest directional match for the direction of the momentum of the two-ball system before they collide. All right, so once again, I have N that way, and I have 4 this way, so that's going to be, atom as vectors is going to be up and to the right. So N makes the most sense. This is probably going to be down and to the left, so it's going to be P. C is going to be nothing. S is to the left a little bit. Identify the closest directional match for the direction of the momentum of the two-ball system after. It has to be conserved. So it'll be exactly the same. Exactly the same. That's what it means to be conserved. All right.